13.8 billion years ago, there was a moment when the universe became visible for the very first time. Not visible to any eye, no eye existed, but visible in the physical sense, transparent light which had been trapped inside a glowing plasma since the first instant of creation was finally released. It streamed outward in every direction simultaneously, and it has never stopped. That radiation is still here. It is passing through your room at this moment. Welcome to Quiet Science at Bedtime. This channel is still very new, and if tonight's story settles you, please consider subscribing, leaving a like, and turning on notifications. It takes only a moment, and it helps more than you might know. Everything on this channel is grounded in real scientific research and current academic understanding. You will never hear anything here that is not rooted in measurable, peer-reviewed reality. Just relax and feel free to let this play as you drift off to sleep. Now, imagine 380,000 years after the Big Bang, the universe cooled through a temperature of approximately 3000 Kelvin, and at that threshold, free electrons and protons combined into neutral hydrogen atoms for the first time. The photons that had been locked inside the plasma were suddenly free to travel. That moment of release is called recombination, and the light it produced has been traveling ever since, cooling and stretching with the expansion of space from near infrared to microwave, arriving at your location tonight at a temperature of exactly 2.725 Kelvin. It surrounds you in every direction with perfect uniformity. This is the cosmic microwave background, and tonight you are not studying it from the outside. Tonight you are inside the moment it was born. You are inside the universe 380,000 years after the Big Bang. There is no ground beneath you. There is no sky above you. There is no horizon in any direction. What surrounds you in every direction you can perceive is a plasma, a fog of matter so hot and so dense that it glows, not with the warm orange of a campfire, and not with the blue-white of a stellar surface. It glows with a deep, all-encompassing red-orange radiance that fills every direction equally. It is not light traveling from a source to a receiver. It is erupting from every point in space simultaneously, absorbed and re-emitted so rapidly that no photon can travel more than a fraction of a millimeter before scattering. There is no transparency here. There is no distance. There is only the luminous, pressurized, electrically charged plasma, moving as a single system in every direction you can conceive. The temperature of the plasma surrounding you is approximately 3020 Kelvin. You should understand what that number means in physical terms. 3000 Kelvin is hotter than the filament of a tungsten light bulb at full brightness. It is roughly half the surface temperature of our sun. It is the temperature at which iron glows a deep cherry red, and you are submerged in an environment at this temperature in every direction, simultaneously. What you are floating inside right now is already profoundly cool compared to what existed before. A few million years earlier in this universe, the temperature of the surrounding plasma was in the tens of thousands of Kelvin. A few 100,000 years before that, millions of Kelvin. The universe has been cooling since its first moment, and it has not stopped cooling yet. The plasma surrounding you is composed of three primary constituents. The first is protons, the nuclei of hydrogen atoms, each carrying a single positive charge, each containing 2 up quarks and 1 down quark, held together by the strong nuclear force, each with a mass of 1.673 times 10 to the negative 27 kilograms. The second is free electrons, moving at thermal velocities commensurate with the surrounding temperature, each one roughly 1,836 times less massive than a proton, each carrying a single negative charge equal in magnitude to the protons. The third is photons. In the plasma surrounding you, photons exist in staggering numbers. For every proton in the universe at this moment, there are approximately 1 billion photons, a ratio set by the physics of the Big Bang itself, specifically by the slight asymmetry between matter and antimatter that allowed matter to survive at all. The exact ratio is 1 baryon per 1.6 times 10 to the ninth photons. The photons surrounding you carry energy, and that energy is constantly being exchanged with the surrounding charged particles. A photon in the plasma around you travels a short distance. At this density, its mean free path is on the order of a fraction of a millimeter, and then it collides with a free electron, is absorbed, and is re-emitted in a new random direction. This process happens billions of times per second per photon. The photons are not motionless. Each one moves at the speed of light between collisions, but because each collision sends them in a new random direction, their net displacement through space over any meaningful timescale is effectively zero. You are surrounded by light that cannot travel, light that is trapped by the very matter it illuminates. This intimate coupling between the photons and the baryons, the collective term for the protons that will soon form hydrogen atoms, defines everything about the space you are floating inside. The two components form what physicists call a photon-baryon fluid. They share energy, they share pressure, they move together as a single dynamical system, and that shared pressure produces something extraordinary. It produces waves, not sound waves in the sense you might experience them, because there is no air, no drum membrane, no ear, but the physical mechanism is mathematically identical to sound. Wherever a slight overdensity of matter exists, a region whereby the statistical fluctuations of the inflationary epoch, slightly more particles occupy a given volume, gravity pulls more matter inward. The compression heats the photon-baryon fluid. That heating increases the radiation pressure. The increased pressure pushes back outward, launching a spherical pressure wave through the surrounding plasma. These waves are propagating through the plasma around you right now. They are called baryon acoustic oscillations, and they have been traveling since the very early universe, at a speed equal to approximately 57% of the speed of light in this particular photon-baryon mixture. This speed, the sound speed of the primordial plasma, is determined by the ratio of radiation pressure to total energy density, a quantity calculable from the known composition of the universe at this moment. The distance these waves have traveled in 380,000 years, called the sound horizon, is approximately 450 light-years in the coordinates of this epoch. When scaled to the current size of the universe, expanded by the factor of 1100 that separates the universe then from the universe now, this corresponds to approximately 500 megaparsecs, or roughly 1.6 billion light-years. Every galaxy survey ever conducted has detected the subtle statistical preference for galaxy pairs to be separated by exactly this distance, the fossilized signature of the acoustic waves moving through the plasma surrounding you at this very moment. You cannot perceive the waves, you cannot hear them, and you cannot feel them, because they are density perturbations on scales of hundreds of light years, operating over time scales of tens of thousands of years. But they are here. They are moving through the plasma around you. You are floating inside the largest resonance structure in the history of the universe, a spherical cavity 380,000 light-years deep in every direction, vibrating at frequencies billions of times below any threshold of human hearing. The temperature fluctuations in the plasma surrounding you are at the level of approximately 30 microkelvin, 1 part in 100,000. If you could map the temperature in every direction simultaneously and color code it, The map would appear almost perfectly uniform, but not perfectly. In the regions where the plasma is very slightly warmer, warmer by 30 millionths of a Kelvin, there is a compression, an acoustic wave passing through. In the regions where it is very slightly cooler, there is a rarefaction, and within these fluctuations, encoded in the pressure and density pattern of the plasma around you, is the blueprint for every large-scale structure the universe will ever produce. Every future galaxy, every future cluster, every filament of the cosmic web, every planet, every ocean, every living thing that will ever look up and ask where this all began. All of it is encoded in a temperature fluctuation of 30 millionths of a Kelvin. The irregularities you are floating among are not random. They follow a statistical distribution called the Harrison-Zeldovich spectrum, a nearly scale-invariant power spectrum of density fluctuations produced during the inflationary epoch. The spectral index of this distribution, measured from the cosmic microwave background by the Planck satellite and denoted by the symbol n sub s, is approximately 0.965. This number is very close to, but measurably different from, exactly 1. That slight departure carries information about the physics of inflation. Specifically, it tells us that inflation had a definite beginning, and that the energy scale at which inflation occurred was likely around 10 to the 16th GeV. These are numbers recoverable from the map of the plasma surrounding you right now, from the temperature differences of 30 microkelvin that exist in every direction. The universe has written its own origin into the light around you, and that light is about to be released. Dark matter is present in the plasma surrounding you, though you cannot detect it by any means available to your senses or to any instrument humanity has yet conceived. Dark matter, which comprises approximately 27% of the total energy density of the universe at this moment, does not interact electromagnetically. It carries no electric charge. It does not emit photons, absorb photons, or scatter them. The photon-baryon fluid moves through the dark matter around you, as if the dark matter were not there. What dark matter does interact with is gravity, and that gravitational interaction has been the silent architect of everything that will follow. In the very early universe, while the baryonic matter was held tightly in place by radiation pressure, prevented from clumping by the outward push of the photon-baryon fluid, the dark matter was already free to respond to gravity alone. It had no radiation pressure coupling to resist. Over hundreds of thousands of years, it assembled itself into shallow gravitational potential wells, regions of slightly enhanced gravitational pull, distributed across space in a pattern determined by the same inflationary fluctuations that produce the acoustic oscillations in the plasma. These potential wells are already in place around you. You cannot see them, feel them, or measure them directly, but they are here, and they are waiting. When recombination releases the baryonic matter from the radiation field, the neutral hydrogen and helium will fall into these pre-existing dark matter structures. The baryons will follow the scaffolding that dark matter has already built, and that scaffolding will determine the locations of the first stars and the first galaxies with a precision that no random process could produce. The dark matter surrounding you has a density of approximately 1.4 times 10 to the negative 27 kilograms per cubic meter. This is less dense than any vacuum achievable in a terrestrial laboratory, and yet across the entire observable universe, it totals a mass of approximately 10 to the 53 kilograms, 27% of the critical density, as precisely measured by the temperature power spectrum of the cosmic microwave background. The number you should hold for a moment is 27%. The ordinary matter, every proton, every neutron, Every atom of hydrogen and helium in the plasma surrounding you constitutes only 5% of the total energy content of the universe at this moment. Dark matter is more than 5 times as abundant as everything you can in principle detect. And dark energy, the component that will, billions of years from now, accelerate the expansion of the universe, constitutes 68%. The plasma you are floating inside, luminous and pressurized, and seemingly total, represents a small minority of what the universe is made of. You are a guest in a universe mostly composed of things you cannot touch. Now consider the recombination threshold approaching. The temperature of the plasma surrounding you has been falling continuously since the first instant of the Big Bang, driven by the expansion of the universe. As space expands, the wavelengths of all photons stretch with it. Each photon loses energy as its wavelength grows, and the energy density of radiation falls with the fourth power of the expansion factor. The matter density falls with the cube of the expansion factor. These two components cool at different rates, but in the photon-baryon fluid, they remain in thermal equilibrium, constantly exchanging energy through scattering, and so the entire fluid shares a single temperature that falls together. That shared temperature is now approaching 3000 Kelvin, and this number matters because it marks the boundary where the thermal energy of electrons drops below the binding energy of the hydrogen atom, where the kinetic energy available in the plasma becomes insufficient to keep the protons and electrons permanently separated. The binding energy of hydrogen in its ground state is 13.6 electron volts. The average kinetic energy of a particle in the plasma at 3000 Kelvin, given by 3/2 times Boltzmann's constant times the temperature, is approximately 0.38 electron volts. These two numbers are very different, and you might expect recombination to occur at a much higher temperature when the average kinetic energy approaches the binding energy. The reason it does not is the photon-to-baryon ratio of 1 billion to 1. At temperatures where the average photon has too little energy to ionize hydrogen, the high energy tail of the photon distribution, the small fraction of photons far above the average energy, still contains enough photons to immediately ionize any hydrogen atom that forms. The plasma stays ionized not because the average photon is energetic enough, but because the sheer quantity of photons ensures that the rare high-energy ones are always present in sufficient number to undo any recombination. This behavior is captured mathematically by the Saha equation, a formula derived from statistical mechanics in 1920 by the Indian astrophysicist Meghnad Saha, originally developed to understand the ionization states of stellar atmospheres. The Saha equation describes the ionization fraction of a gas in thermal equilibrium as a function of temperature and particle density. Applied to the conditions of the early universe, it predicts that the transition from a fully ionized plasma to a mostly neutral gas occurs over a temperature range of roughly 500 Kelvin from approximately 3500 Kelvin, where 90% of protons remain ionized, down through 3000 Kelvin, where the ionization fraction has fallen to roughly 50%, continuing to approximately 2500 Kelvin, where it drops below 1%. This transition, called recombination, takes place over tens of thousands of years. It is not an event, it is a process, a gradual tipping of a balance that has been stable since the universe was a fraction of a second old. And the tipping is beginning now in the plasma surrounding you. You become aware, not through sensation, but through the precision of the physics, that something is changing in the space around you. In each cubic meter of plasma, electrons and protons are occasionally finding each other, pulled together by the electromagnetic force. They approach, an electron enters the quantum influence of a proton and begins to cascade downward through the energy levels of hydrogen, emitting a photon at each transition, losing energy at each step, falling toward the ground state. Most of these newly formed atoms are immediately destroyed. A nearby high-energy photon strikes the electron and strips it away again. The ionization fraction falls, then recovers slightly, then falls again. But the trend is irreversible. At 3020 Kelvin, the process of recombination has begun to tip the balance, and nothing will reverse it. Each hydrogen atom that forms does so through the process of radiative recombination, a quantum mechanical cascade through the energy levels of hydrogen. The energy levels of hydrogen are quantized at specific values determined by the principal quantum number n. The ground state, n equals 1, has a binding energy of 13.6 electron volts. The n equals 2 state has a binding energy of 3.4 electron volts. The n equals 3 state, 1.51 electron volts. The transition from n equals 2 to n equals 1, known as the Lyman alpha transition, produces a photon of wavelength 121.6 nanometers. In the ultraviolet, the transition from n equals 3 to n equals 2, the H alpha transition, produces a photon at wavelength 656 nanometers. In the deep red, these transitions are occurring around you. Photons of specific wavelengths are being emitted by the cascading electrons, then immediately absorbed by nearby atoms, then re-emitted in a different direction. The plasma is still opaque, but there is a complication in the recombination process that slows it. The Lyman alpha photon produced when an electron falls to the ground state carries exactly enough energy to ionize another ground state hydrogen atom. In the dense plasma of the early universe, any Lyman alpha photon produced is almost immediately absorbed by a neighboring atom, undoing the recombination. Efficient recombination to the ground state is blocked. Instead, recombination proceeds primarily through a rare quantum mechanical process called two-photon decay. A hydrogen atom in the metastable 2Z state, a state that cannot decay through a single Lyman alpha photon because of quantum selection rules, decays to the ground state by emitting two photons simultaneously. The two photons share the transition energy between them in a continuous distribution, and crucially, neither photon has enough energy individually to ionize another hydrogen atom. This two-photon decay process has a rate of approximately 8.2 per second, extremely slow by atomic physics standards. But the universe contains so many hydrogen atoms that even at this rate, neutral hydrogen forms across the entire observable universe at a pace of trillions upon trillions of atoms per second. The universe is recombining, slowly, steadily, and it has not recombined before. You should note that the helium in the plasma surrounding you has already recombined. Helium, which constitutes approximately 24% of the baryonic matter by mass, a fraction established during the first 3 minutes after the Big Bang in the epoch of Big Bang nucleosynthesis, has a first ionization energy of 24.6 electron volts and a second ionization energy of 54.4 electron volts. Both are substantially higher than hydrogen's 13.6 electron volts, and so helium reached its neutral state at a temperature of approximately 12,000 Kelvin, around 50,000 years before the hydrogen recombination you are witnessing now. The helium around you is already quiet, already neutral, already transparent to most radiation, already following gravity rather than radiation pressure. Only the hydrogen, which makes up approximately 76% of the baryonic matter by mass, remains partially ionized. There is also a trace of deuterium in the plasma around you, heavy hydrogen, with one neutron alongside the proton, at a concentration of approximately 25 parts per million by number relative to hydrogen. This ratio is a precise measurement of the total baryon density of the universe. A higher baryon density produces more neutrons relative to protons and more complete deuterium burning into helium, lowering the surviving deuterium fraction. The measured deuterium abundance constrains the baryon density to better than 1%, and there is lithium-7 at a level of approximately 2 to 3 atoms per 10 billion hydrogen atoms, predicted by Big Bang nucleosynthesis, and measurable in the spectra of the oldest surviving metal-poor stars. The universe at this moment contains hydrogen, helium, deuterium, and a trace of lithium. Nothing heavier exists anywhere in the universe. Every carbon atom, every oxygen atom, every iron atom, every molecule of every kind, none of it exists yet. It will be forged in the cores of stars that have not yet formed, in a universe that is not yet transparent, in a future that is encoded in the fluctuations of the plasma surrounding you but has not yet arrived. You are in the universe before the elements. You are at the last moment of the simplest universe that will ever exist. The temperature falls through 2900 Kelvin. The ionization fraction, the ratio of free electrons to total protons, has dropped to 30%. Each cubic meter of plasma surrounding you now contains roughly 300 million free electrons, down from 1 billion just tens of thousands of years earlier. The mean free path of a photon has grown from fractions of a millimeter to centimeters, then to meters. The plasma is still opaque to any observer inside it, but the scattering rate is falling. Photons in the plasma around you are beginning to travel farther between collisions. Not freely, not yet, but farther than before. 2800 Kelvin. The ionization fraction falls to 20%. The photon spectrum surrounding you remains a near-perfect blackbody. The Planck distribution, because thermal equilibrium is still maintained within the plasma. The scattering rates, though decreasing, are still high enough to prevent the spectrum from departing from its thermal form. The universe is cooling uniformly. Every region of the plasma around you is at the same temperature, within 30 microkelvin. Every cubic meter at the same density, within 1 part in 100,000, 2700 Kelvin, 10% ionization. Each cubic meter of plasma surrounding you now contains roughly 100 million free electrons. The mean free path of a photon is growing toward hundreds of light years. These are still not the conditions of transparency. A photon cannot travel from where you are to any visible horizon before scattering, but the fog is thinning. 2600 Kelvin, 4% ionization. The free electron density has fallen by a factor of 25 from its value at the beginning of recombination. The mean free path of a photon has grown to thousands of light years. The universe is not yet transparent, but it is becoming translucent in a way that has no precedent in the history of everything that has existed before this moment. The photons being created around you now, in the 2-photon decays of hydrogen 2s states, in the cascade recombinations through higher energy levels, are traveling significant distances before scattering. Some of them will not scatter again. The surfaces from which photons last scatter, before streaming freely, will be remembered in the universe for as long as the universe exists. Each of those photons will carry the temperature and density of its last scattering surface, encoded in its direction and wavelength, as it streams freely through the expanding cosmos. 2500 Kelvin, 1% ionization. At this point, The mean free path of a photon exceeds the size of the observable universe. There are no longer enough free electrons in the plasma around you to intercept the light. The universe, which has been opaque since its first instant for 380,000 years, becomes transparent. The photons are free. You notice the change before you can describe it. The plasma that surrounded you in every direction, that pressed its glow against your perception from everywhere simultaneously, begins to recede. Not all at once, not in a flash, across tens of thousands of years, compressed here into a single moment of perception. The fog lifts. Where there was once a uniform wall of glowing plasma at close range, there is suddenly depth. The glow is still there, but it is no longer adjacent. It is distant. It is retreating on the expansion of space, fading into what will become the horizon of the observable universe. Photons from the last scattering surfaces are arriving at your location from enormous distances, carrying with them the image of the plasma as it was at the moment of their last collision. This is the surface of last scattering. It is not a physical surface. There is no wall, no membrane, no boundary you could touch. It is a temporal surface, a moment in time, smeared over a finite range of temperatures, from approximately 3,500 Kelvin down to 2,500 Kelvin, corresponding to the range over which the ionization fraction fell, from 90% to 1%. Every photon in the cosmic microwave background has its origin on this surface. When the Planck satellite mapped the CMB with its arrays of microwave detectors cooled to 100 millikelvin, 1/10 of a degree above absolute zero, it was mapping this surface. It was imaging the plasma around you at this moment from a vantage point 13.8 billion years in the future. The CMB photons now streaming freely around you are departing in every direction. Those that travel in what will eventually be the direction of Earth will arrive there in 13.8 billion years. They will strike the horn antenna of a radio telescope operated by two engineers in Holmdel, New Jersey, in the year 1964. The engineers will find an unexpected microwave signal, a noise equal in every direction, impossible to eliminate, corresponding to a temperature of approximately 3.5 Kelvin. The measurement will be traced, refined, and recognized as the thermal remnant of the plasma you are inside tonight. The discovery will be awarded the Nobel Prize in Physics in 1978. A group at Princeton will independently predict the existence of this radiation from theoretical considerations at the same time, and will hear of the Holmdel measurement just before publishing their prediction, too late to make the first experimental claim. The moment of recombination occurring around you now will, in 13.8 billion years, be recognized as one of the most important observational discoveries in the history of science. But the photons have not arrived there yet. They have just been released. They are streaming outward from the surface of last scattering in every direction, carrying with them the image of the plasma at 3,000 Kelvin. And they will not stop. They will not scatter again, not in any significant sense. They will travel through the expanding universe, stretched by that expansion, losing energy as their wavelengths grow, cooling from near-infrared to microwave, to longer wavelengths still. For as long as the universe expands, the CMB photons surrounding you at this moment carry an energy density of approximately 4 times 10 to the negative 14 joules per cubic meter. As the universe expands by a factor of 1100, this energy density will fall by a factor of 1100 to the 4th power, by 1100 squared, because the volume increases, and by an additional factor of 1100 squared, because each photon's energy decreases with the stretching of its wavelength. The temperature, which scales as the inverse of the expansion factor, will fall from 3000 Kelvin to 3000 divided by 1100, which equals approximately 2.725 Kelvin. This is the temperature of the CMB in your room tonight, 2.725 Kelvin. Exactly. This number has been measured with extraordinary precision by the PHERIS instrument aboard the COBE satellite, which observed the CMB spectrum from 1989 to 1993 and determined the temperature to be 2.7255 Kelvin with an uncertainty of less than 1 millikelvin. The CMB spectrum measured by PHERIS was so precisely blackbody, so perfectly consistent with a Planck distribution, that the deviation from a perfect thermal spectrum was found to be less than 50 parts per million. It remains the most perfect blackbody spectrum ever measured from a natural source. The light you are surrounded by now is that spectrum at its origin temperature. You are watching the most perfect blackbody in the observable universe being released. The peak of the Planck distribution at 3000 Kelvin falls at a wavelength of approximately 966 nanometers. In the near infrared, just beyond the red edge of the visible spectrum, the visible portion of the emission peaks in the deep red near 700 nanometers. This is why the plasma surrounding you glows red-orange. Not because it has any pigment or surface color, but because the thermal emission spectrum of a 3000 Kelvin blackbody peaks in frequencies corresponding to deep red light. Every photon being emitted by the plasma around you is produced by this same mechanism, the thermal agitation of charged particles producing electromagnetic radiation at a rate and spectral distribution determined entirely by the temperature. This is the color of a universe becoming transparent. You look around, or hold the concept of looking around, since there is no body here, only awareness, and in every direction, the receding glow of the surface of last scattering is visible. It is not moving away from you in space. The surface is at a fixed moment in time, the moment of last scattering, and the photons from that surface are arriving at your location from increasingly distant regions as time passes. The surface appears to surround you because it does surround you in every direction at every point in the sky. This is not a property of your location. Every location in the universe is surrounded by the surface of last scattering equally. The universe has no center, no preferred vantage point, no special location. The CMB arrives from all directions equally at every point in space. You are not at the center of the universe, you are at a center, as every point in the universe is. In the coordinates of the modern universe, the surface of last scattering is located approximately 45 billion light-years away, in every direction. This number, larger than the age of the universe in light-years, reflects the expansion of space since the moment of emission. The region of the universe from which the CMB photons you observe tonight were emitted was, at the moment of their emission, approximately 40 million light-years away. But in the 13.8 billion years since recombination, the expansion of space has carried that region to a current distance of 45 billion light-years, while the photons themselves cross the expanding distance between. The photons you detect carry the image of matter that is now 45 billion light-years away, matter that cannot be seen in any other way, because all light emitted after recombination from that distance has not yet had time to reach us. The surface of last scattering is the boundary of the observable universe. Beyond it, in the direction of earlier times, the universe is opaque. This moment, this release, is the limit of how far back any photon-based observation can reach. You are at the limit, you are at the edge of everything that can be seen. The information carried by the CMB photons, now streaming freely around you, is not incidental. It is structural. Each photon carries, encoded in its precise wavelength and direction of travel, a record of the density and temperature of the plasma at its point of last scattering. You can understand what that record contains by considering the three physical effects that imprint themselves on the photons as they escape from the last scattering surface. The first effect is gravitational. In the regions of the plasma surrounding you, where matter is very slightly denser by 1 part in 100,000, there exists a shallow gravitational potential well, a photon created at the bottom of that well and streaming outward toward its long journey through the cosmos, must climb out of the well as it travels. Climbing out of a gravitational well costs energy. The photon loses energy. Its wavelength lengthens slightly. It appears to a future observer very slightly cooler than average. This effect, the gravitational redshifting of photons escaping from overdense regions, is the dominant contribution to the large-scale temperature anisotropies in the CMB. The slightly cooler spots in the CMB map correspond, on the largest scales, to the locations of the largest future structures, the galaxy clusters and superclusters that gravity will spend billions of years assembling. The second effect is the intrinsic temperature fluctuation. The slightly denser regions of plasma are in general slightly hotter because compression heats the fluid. So a photon emitted from an overdense region begins with a slightly higher temperature before the gravitational redshift, and a photon emitted from an underdense region begins with a slightly lower temperature. These two effects, the temperature fluctuation and the gravitational redshift, partially cancel each other on the largest scales. Their combined contribution is called the Sachs-Wolf effect, named for the two physicists who calculated it in 1967. The third effect is Doppler. At the moment of last scattering, the plasma in different regions is moving at different velocities, flowing inward toward overdensities under gravitational attraction, or flowing outward as acoustic waves propagate. A photon emitted from a region of plasma that is, at the moment of emission, moving toward the observer is slightly blue-shifted, its wavelength compressed slightly, its apparent temperature slightly elevated. A photon from plasma moving away from the observer is slightly redshifted. These Doppler contributions are most significant on intermediate angular scales, where the acoustic peaks of the CMB power spectrum are located. The combination of all three effects, gravitational, intrinsic thermal, and Doppler, produces the pattern of temperature fluctuations that covers the last scattering surface surrounding you. Mapped onto the sphere of the sky, this pattern has a specific statistical structure, the angular power spectrum of the CMB. When this spectrum is measured, as it has been with extraordinary precision by the Planck satellite, it shows a series of peaks and troughs at specific angular scales. The first acoustic peak appears at an angular scale of approximately 1 degree on the sky, the second peak at approximately half a degree, the third at approximately 1/3 of a degree. Each peak corresponds to a harmonic of the fundamental acoustic oscillation in the plasma, the mode for which exactly 1, 2, or 3 half wavelengths of the pressure wave fit within the sound horizon at the moment of last scattering. The positions of these peaks are sensitive to the geometry of the universe. In a spatially flat universe, one in which the total energy density equals the critical density, light travels in straight lines, and the angular size of the sound horizon at last scattering corresponds to approximately 1 degree. The fact that the first acoustic peak is observed at almost exactly 1 degree is one of the most precise measurements of the spatial geometry of the universe ever made. It tells us that the universe is flat, or very nearly so, to within half of 1%. The flatness of the universe is a consequence of the inflationary epoch, the period of exponential expansion in the first tiny fraction of a second after the Big Bang that stretched any initial curvature to negligible levels. You are floating inside the last scattering surface. Around you, in every direction, the plasma is releasing its photons for the first time. The pattern of temperature fluctuations you are surrounded by, 30 microkelvin above average in some directions, 30 microkelvin below average in others, is the same pattern that will be observed from Earth in 13.8 billion years and used to determine, to 6 significant figures, the basic parameters describing the entire observable universe. 6 numbers, 6 cosmological parameters, and all 6 are readable from the map of the light being created around you now. The first is the total energy density, found to be equal to the critical density to within 0.5%, confirming spatial flatness. The second is the baryon density, found to be approximately 4.9% of the critical density, consistent with the deuterium abundance and Big Bang nucleosynthesis predictions. The third is the cold dark matter density, found to be approximately 26.8% of the critical density. The fourth is the dark energy density, found to be approximately 68.3%, consistent with the cosmological constant and the late-time acceleration of the universe's expansion. The fifth is the amplitude of the primordial power spectrum, the overall magnitude of the density fluctuations produced during inflation, which sets the overall level of structure formation. The sixth is the spectral index, 0.965, which sets the slope of the primordial fluctuation spectrum and carries information about the dynamics of inflation itself. 6 numbers that describe a universe of 2 trillion galaxies. 6 numbers readable from the 30 microkelvin temperature fluctuations of the plasma surrounding you at this moment. There is a particular consequence of recombination that operates on cosmic scales and leaves its signature in the distribution of matter throughout the entire history of the universe. The baryon acoustic oscillations, the pressure waves propagating through the photon-baryon fluid around you, have been traveling since the earliest moments of the universe. At the moment of recombination, when the photon pressure that drove them is removed, they freeze. The pattern of compressions and rarefactions that exists in the plasma at this moment is locked into the distribution of baryonic matter. The sound horizon at last scattering, approximately 450 light-years in the coordinates of this epoch, corresponding to 500 megaparsecs in the coordinates of the modern universe, becomes imprinted as a preferred scale in the spatial distribution of matter. Galaxy surveys measuring the positions of hundreds of millions of galaxies across the sky have detected this imprint as a subtle statistical excess in the probability of finding 2 galaxies separated by exactly this distance. The baryon acoustic oscillation feature in the galaxy power spectrum serves as a standard ruler for measuring the expansion history of the universe, a scale whose physical size is known from CMB measurements, and whose apparent angular size or redshift separation in galaxy surveys can be used to measure the distance-redshift relation and constrain the properties of dark energy. The waves frozen in the plasma around you tonight are the same waves detected in galaxy surveys conducted billions of years from now. The connection between this moment and those surveys is direct and unbroken. The physics is continuous. The plasma releases its photons. The baryons follow the dark matter into the potential wells. The acoustic scale is preserved in the matter distribution, and billions of years later, the distribution of galaxies still carries the echo of the waves that are propagating around you at this moment. You are inside an echo that will outlast every star. Now the universe around you continues to cool. The temperature falls through 2200 Kelvin. The glow has shifted entirely into the infrared. The thermal emission of the plasma is no longer in the visible range. To any observer equipped with only human eyes, the universe is becoming dark even before the photons have fully decoupled, because the peak of the Planck distribution at 2200 Kelvin falls at approximately 1300 nanometers, well into the infrared, and only the long tail of the spectrum still reaches into the red end of the visible range. The universe is dimming, not suddenly, not in a flash, in the quietest possible way, a gradual shift of the thermal emission spectrum toward longer wavelengths, as if a lamp were being slowly tuned to a frequency the eye can no longer register. 2000 Kelvin. The ionization fraction is now below 1/10 of 1%. The plasma is almost entirely neutral. The photon-baryon fluid has decoupled. The two components that have been coupled together since the first second of the universe have separated, and from this point forward, they will evolve independently. The matter will follow gravity. The radiation will follow the expansion of space. The universe has just divided itself into two separate stories. One story belongs to the matter, the neutral hydrogen and helium falling into the dark matter potential wells, slowly assembling into the first stars and galaxies over the next 150 million years. That story is full of eventual drama, the ignition of the first stars, the reionization of the intergalactic medium by their ultraviolet radiation, the formation of the first black holes, the slow hierarchical assembly of the first galaxies. It is a story of increasing complexity, increasing brightness, increasing diversity. The other story belongs to the radiation, to the photons streaming freely through the expanding universe, cooling and stretching with no further interaction with matter, carrying their encoded information through 13.8 billion years of cosmic expansion until they arrive at the instruments of a species of beings who evolved on a rocky planet orbiting an ordinary star in an ordinary galaxy, who built instruments sensitive enough to measure them and who read from them the entire history of the universe's beginning. Both stories began in the plasma around you. Both are encoded in the fluctuations of 30 microkelvin, and you are present at the fork where they separate. The CMB photons passing through your room at this moment, in the real present as you lie still, are not the warm near-infrared photons streaming freely around you inside this story. They are the same photons, 13.8 billion years older, stretched by the expansion of the universe by a factor of 1100. At 2.725 Kelvin, each CMB photon arriving at your location tonight carries a wavelength of approximately 2 millimeters and an energy of approximately 2.3 times 10 to the negative 4 electron volts. This is far below the energy threshold required to excite any chemical bond, ionize any atom, or trigger any biological response. CMB photons interact with ordinary matter at a rate of approximately 1 collision per meter of travel through water-equivalent material. Through air, the interaction rate is orders of magnitude lower. Through your body, the vast majority of the approximately 500 CMB photons crossing each square centimeter of your skin every second pass without interaction of any kind. You are bathed in the oldest light in the universe. You cannot feel it. It does not warm you. It does not disturb you. It passes through your walls, through your body, through the earth beneath you, as if none of those things were there. But it is present. It has always been present, everywhere since the moment of its release, 380,000 years after the Big Bang. It is present between the galaxies. It is present inside them. It is present in the space between the atoms of your skin. It fills the universe isotropically, equally in every direction, to within 1 part in 100,000. and it will continue to do so for as long as the universe exists. The CMB photons you are surrounded by inside this story, at 3000 Kelvin freshly released, are the same photons. You are present at their birth and in their presence simultaneously. The past and the present share the same light. The universe surrounding you continues to cool, 1800 Kelvin. The neutral hydrogen formed during recombination is settling. The electrons in ground-state hydrogen atoms now occupy the 1s orbital, a spherically symmetric probability distribution centered on the proton with a mean radius of 53 picometers. This is the Bohr radius, the fundamental length scale of the hydrogen atom, defined by the balance between the electron's kinetic energy and its electromagnetic attraction to the proton. The electron in the ground state cannot fall to a lower energy level. There is no lower level available in the quantum structure of hydrogen. The atom has reached its most stable configuration. It will remain this way until it encounters another atom or a photon energetic enough to cause an upward transition. At the falling temperatures of the universe around you, encounters energetic enough to disturb a ground state hydrogen atom are becoming rare. The photons streaming freely have already departed the last scattering surface and are traveling outward at the speed of light. The photons remaining in the vicinity, the tail of the thermal distribution, now very faint, carry progressively less energy as the temperature falls. The neutral hydrogen is becoming stable. The universe is becoming chemically simple. Two atoms, hydrogen and helium, and nothing else anywhere. The universe around you is settling into a state of almost perfect simplicity. 1500 Kelvin. The thermal glow is gone from the visible spectrum entirely. The universe is dark to any eye. The CMB photons are streaming freely in every direction, cooling and receding. The neutral hydrogen and helium gas fills the universe at a density of approximately 2,000 atoms per cubic meter, less dense than the best laboratory vacuum achievable on Earth. The dark matter fills the same volume at its own density, invisible and gravitational, already beginning the slow work of pulling the baryonic gas into its potential wells. Gravity is patient. It does not hurry. It operates at the speed at which information travels through a gravitational field, at the speed of light, but the structures it is building are large, and the overdensities driving their formation are tiny. 1 part in 100,000. It will take gravity approximately 150 million years to amplify these fluctuations enough to produce the first stars. The universe has a long time to wait in the dark. You are inside that waiting. The dark ages of the universe, the period between recombination and the first stellar ignition, will last approximately 150 million years. During this entire interval, there will be no source of visible light anywhere in the universe, no star, no galaxy, no burning gas cloud. The universe will be illuminated only by the fading infrared of the CMB, redshifting steadily toward microwave wavelengths, dimming energy by energy, imperceptible to any biological eye. The 21-centimeter hyperfine transition of neutral hydrogen, the photon emitted when an electron flips its spin relative to the proton, with a wavelength of exactly 21.1 centimeters and an energy of 5.9 times 10 to the negative 6 electron volts, will be the only electromagnetic emission of the neutral gas during this entire epoch. The time scale for this transition is 11 million years on average for any individual atom, but with enough atoms, the cumulative 21-centimeter emission of the cosmic dark ages will be detectable by future radio telescope arrays, sensitive enough to observe it. The dark ages are long, but they are not empty. Gravity is working in the dark. Dark matter is assembling its structures. The baryonic gas is falling slowly along the filaments of the dark matter web. The future is being constructed, invisible in the cold 1200 Kelvin. The universe is very cold now, cold in absolute terms, cold compared to the surface of any star, cold compared to the plasma you were just inside. 1000 Kelvin. The thermal radiation is entirely in wavelengths far beyond the visible. 800 Kelvin. The universe is quiet and dark and expanding. Let the pace of this story slow to match it. There is no urgency in the dark ages. There is only time, large amounts of time. The universe has already produced everything it needs to produce the future. The dark matter web, the baryonic gas, the acoustic imprint in the matter distribution, the freely streaming CMB, everything required to build the observable universe of the present moment already exists, in potential, in the cooling gas and invisible structure around you. It merely needs time. 600 Kelvin. The universe expands. The CMB cools. The gas follows gravity. The dark matter structures grow. 500 Kelvin. You allow your awareness to rest on the simplicity of what surrounds you. Hydrogen and helium, dark matter, freely streaming photons, expanding space. These are the only actors. There is no chemistry yet. No molecules have formed because the gas is still too warm and too diffuse for hydrogen to bond with itself into molecular form. Molecular hydrogen, H2, the simplest possible molecule, will begin forming in appreciable quantities only when the temperature of the gas falls below a few hundred Kelvin and the density in overdense regions rises enough to allow three-body collisions. That is still in the future. For now, the universe is atomic, the simplest possible collection of matter in the simplest possible states. 400 Kelvin. The sentences around you grow shorter as the universe quiets. 300 Kelvin. The gas temperature is now approaching room temperature, the temperature of the air around you as you listen. The early universe, so unimaginably hot and dense in its first moments, has cooled to a temperature you could in principle survive. Not that there is air to breathe, or ground to stand on, or pressure to support your body, but the raw thermal energy of the radiation field around you has cooled to a scale familiar from daily life. 200 Kelvin. The universe is colder than a winter night, colder than the surface of Mars. The CMB photons continue to stream. Gravity continues to work. 150 Kelvin. The dark matter web is growing. The baryonic filaments are beginning to fall along it. In overdense regions, the gas is compressing slightly as it falls toward the centers of the largest potential wells. The compression is gentle, too gentle to produce any heat visible on cosmic scales, but it is happening. The future is being built, one falling atom at a time, in a universe with no light and no warmth and no chemistry and no complexity. The first star is still 150 million years away, but the gas is falling, and gravity does not stop. You do not need to follow the universe into the dark ages tonight. You have already been inside the most significant transformation in the history of the early cosmos. You have been inside the plasma at 380,000 years, at 3000 Kelvin, at the moment the photon-baryon fluid decoupled, and the light that had been locked inside matter since the first instant of the Big Bang was finally free to travel. You have watched the ionization fraction fall through the predictions of the Saha equation, seen the two-photon decay of hydrogen 2s states allow recombination to proceed to completion, understood the freezing of the baryon acoustic oscillations, and the encoding of the sound horizon into the matter distribution. You have been present at the surface of last scattering, where every CMB photon in the observable universe was released, carrying the image of this plasma, of this moment, to every observer in every direction for as long as the universe expands. You know what the cosmic microwave background is now, not as an abstraction, but as a physical reality you have been inside. It is the thermal emission of a plasma at 3000 Kelvin, redshifted by the expansion of the universe by a factor of 1100, arriving at your location tonight from every direction at a temperature of exactly 2.725 Kelvin. It is the most perfect black body spectrum ever measured from a natural source. It is the oldest directly observable light in the universe, and it is passing through your room at this moment, through your walls, through the air around you, through the space between your thoughts, 500 photons per square centimeter per second. Every second, in every direction. It has been doing this since 380,000 years after the Big Bang. It will continue doing this for as long as the universe expands. There is something to hold in the stillness of this moment. Every proton in your body was present in the plasma you have just been inside. Each one has existed since the first second after the Big Bang, moving through the quark-gluon plasma of the first microseconds, surviving the hadronic epoch, participating in the photon-baryon fluid, falling silent into neutral hydrogen at the moment of recombination, drifting through the dark ages, eventually collapsing into the first stellar clouds, being processed through stellar nucleosynthesis across multiple generations of stars, scattered by supernovae into the interstellar medium, incorporated into the solar nebula of our sun, settling into the crust of a planet, dissolved into an ocean, incorporated into organic chemistry, and finally arriving in you, the most recent address of a proton that has existed for 13.8 billion years. The heavier elements in your body, the carbon in your cells, the oxygen in your lungs, the calcium in your bones, the iron in your blood, were forged in the interiors of stars. Stars that lived and died before the sun was born. Stars whose ashes were scattered by stellar winds and supernovae into the interstellar medium and eventually drawn into the solar nebula that became our solar system. You are made of the material from at least 2 or 3 generations of stellar evolution, but the hydrogen in you is older than any star. It was here, in the plasma, in the photon-baryon fluid, in the moment of recombination, in the oldest light. You are not separate from the universe you have been inside tonight. You are a continuation of it. That is not a metaphor, it is chemistry, physics, and the known history of every atom in your body. Let this ground you now as the story moves toward its close. The CMB photons are streaming past you in every direction. They have been doing so since the moment you were born. They will continue after you are gone. 2.725 Kelvin, arriving from every direction, present in every cubic centimeter of the space you occupy. You cannot feel them. They do not warm you or disturb you, but they are there. The universe is in contact with you through the oldest light it has ever produced, and it has been in contact with you in this way since before you drew your first breath. The universe is vast, 2 trillion galaxies, 100 billion stars per galaxy, on average, observable diameter of 93 billion light years, age of 13.8 billion years, total baryonic mass of approximately 10 to the 53 kilograms, composed at the largest scales of 68% dark energy, 27% dark matter, and 5% ordinary matter, the matter of which you are made. The 5% is enough. The universe is old, and it is expanding, and it is very cold in the spaces between the stars. At 2.725 Kelvin, the CMB is the coldest large-scale thermal signal in the observable cosmos. The universe is colder than it has ever been, and growing colder still as dark energy accelerates the expansion and carries galaxies beyond each other's observable horizons. In the very far future, timescales of trillions and quadrillions of years, the last stars will exhaust their fuel, the last black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy, uniformly cold, uniformly dark, with only the CMB remaining, redshifted far below any frequency measurable by any conceivable instrument, carrying the last faint record of the plasma you have been inside tonight. But that is not tonight. Tonight, the CMB is 2.725 Kelvin, measurable, mapped, known. Tonight, you have been inside the moment it was born. Let your breathing slow. The universe around you, the physical universe, the one your body occupies, is expanding at a measured rate of approximately 67.4 kilometers per second per megaparsec. Every megaparsec, every 3.3 million light years of distance between you and a distant galaxy adds 67.4 kilometers per second to the recession speed of that galaxy. The universe is not rushing. It is not explosive in its present form. It is steady, measured, quiet at the largest scales. The expansion is carrying everything gently apart, including the thoughts you are thinking now, including the air in your lungs, including the atoms that will, over billions of years, drift farther and farther from each other as the space between them grows. Nothing is lost. Everything is redistributed. The universe is very good at conservation. Energy is conserved. Baryon number is conserved. The information encoded in the CMB photons streaming past you tonight, the 30 microkelvin temperature fluctuations, the acoustic peaks, the Sachs-Wolf signature, is conserved in the sense that it remains encoded in the photons, unchanged, for as long as those photons travel through empty space. The oldest information in the universe is still intact. You were there when it was written. The pace of the story has slowed. The sentences are shorter now. The science remains real, but it is held more gently. This is how the universe sounds when it is very cold and very quiet, not silent. The CMB fills the space, but quiet in the way that a temperature of 2.725 Kelvin is quiet, almost, but not quite, at the lowest possible energy. Almost, but not quite. There is still energy here, still information, still the faint, ancient, perfectly black body glow of a universe that was once 3000 Kelvin and is slowly, patiently cooling toward its long future. You're resting inside the expansion. The baryon acoustic scale, 500 megaparsecs, is present in the structure of the universe around you, imprinted in the distribution of matter, readable in the clustering of galaxies. The CMB is present, streaming in every direction at 2.725 Kelvin. The dark matter is present, comprising 27% of the energy density, holding the large-scale structure together gravitationally, and you are present, a structure assembled from the atoms of the early universe, observing the history of the cosmos through a story grounded in physics that is real and measured and known. The plasma has fully dissolved. The universe is neutral. The photons are free. Everything is moving apart, gently, at the measured rate of 67.4 kilometers per second per megaparsec. The gas is cooling. Dark matter wells are deepening, slowly, over millions of years. The first stars are still far in the future, and you are resting. The CMB is 2.725 Kelvin. It is everywhere. It is in your room. It is passing through you at this moment, through the air, through your skin, through the space between your atoms, 500 photons per square centimeter per second, carrying the temperature of a universe at 3000 Kelvin from 380,000 years after the Big Bang, stretched and cooled by 13.8 billion years of cosmic expansion, arriving here, now, in the dark. You were inside the moment those photons were born. You were inside their arrival. They connect both moments. The universe is 13.8 billion years old, and it is still expanding, and the light from its first transparency is still traveling, and it is here. Let that be enough. Let the expansion continue without you. For tonight, let the cooling proceed at its measured rate. Let gravity work slowly in the dark, as it has for 13.8 billion years, assembling the future from the acoustic seeds imprinted at the moment you have been inside. You are resting. The physics continues. Both things are true at once, and they do not conflict. The universe is very large, and very old, and very cold, and the spaces between the stars, and the oldest light it ever produced is present in your room, and you are here, and that is enough. Good night. Thank you for spending this night inside the oldest light in the observable universe, inside the moment 380,000 years after the Big Bang, when the cosmic microwave background was first released and the universe became transparent for the first time. The temperature was 3000 Kelvin. The photons were freed, and that light has been traveling ever since, arriving at your location tonight at exactly 2.725 Kelvin from every direction through everything as it always has. All of the science in tonight's story is real. Every temperature, every ratio, every physical mechanism described here is grounded in current astrophysical research and peer-reviewed measurement. The Saha equation is real. The baryon acoustic oscillation scale is real. The 2-photon decay of hydrogen 2s states is real. The Planck satellite measurement of the CMB temperature is real. The universe becoming transparent is real. And the CMB passing through your room right now, 500 photons per square centimeter per second at 2.725 Kelvin, is real. If tonight's story brought you something true and restful, please consider subscribing to Quiet Science at Bedtime. The channel is still new, and every like, every subscription, and every notification bell turned on helps new listeners find their way here. There is more to come, more moments, more scales, more real science told slowly, in the dark, for the purpose of rest. Sleep well. Good night.